Hello, so here we are. Looks like we're going to be in this mode for a while, so maybe for the whole duration. So I've set up the best I can here, and we'll see how it goes. As you can tell, I posted the draft, I posted the model updating challenge. I debated for a little while whether to make it somewhat more complicated, because it's kind of easy, but I decided to err on the easy side given the circumstances that we're dealing with. If you finish it soon and have no problems, which I hope there won't be many, we might, if we have enough time, add a little layer afterwards, say a part 2 or something like that, to throw a wrench, make it a little bit more challenging. In any case, what I'm going to do now, I was debating whether to actually capture the laptop, which I'm sure that's possible, and just post the, what I see in the laptop as I'm running stuff. But then, after thinking about it a little bit, maybe that's not the best idea for the lecture. It's maybe better to stay conceptual and to describe theory. So here we go. In the last lecture, I think we've already have repeated this a number of times, and so I'm going to complete it now. We begin with data. And for our case, that data, it's actually a force vector, right? Which is real. Okay, this thing is a force vector that it's real, that has, let's say, n steps by 1. If we write it as a column, could be 1 row. No, actually, that's not true. That's not what I mean. Could be, where is my eraser here? That's another thing, the erasing this board doesn't erase well, so I have to use this towel and clean the board every once in a while. But this will have r rows by number of steps, right? So our loading as a matrix is something like this, right? So there are r inputs in general, and we have these inputs over n steps. Those inputs are inputs that we apply to the structure, and we have a number of sensors, and these sensors measure the output. And the output is also real, and if we organize it in rows, it would have n rows, and it would also have generally ns outputs, time stations. And so it would be like this, right? So we have m rows and ns number of steps. So that's the input, that's the output. Needless to say, in some experiments, you could have that the loads are 0 for the last 2 or 3 seconds. The output will not be 0 for the last 2 or 3 seconds because the structure continues to vibrate, right? But in any case, we have input and output, and that's our data which start. Then, from the data, the first thing we do is we obtain observer Markov parameters, right? Now the observer Markov parameters, as we've stated many times, are a zip file for the Markov parameters. Now, how many observer Markov parameters are not 0? Let's say we call them P. Now, how many observer Markov parameters are not 0 is a user's choice. The number of observer Markov parameters that are not 0, when it's multiplied by the number of outputs, must be greater than the order of the system. Now, n is the order. What we mean by the order is, in general, 2 times the number of degrees of freedom. Okay? But remember, we are in a context of system identification. We do not know how many degrees of freedom the system has. We may in an academic setting here, but in general we're saying we don't know how many degrees of freedom the system has. So we don't really know this order. But the beauty of this thing is that it doesn't say anything has to be equal to anything, this just has to be bigger. So since we know the system that we're dealing with, we can say, well, okay, the order is, 20, 10 degrees of freedom, 20, and so on. Therefore, we can choose a minimum P on that basis. Most importantly, or not most importantly, but more realistically, when noise comes into the game, we really cannot expect that from system identification, given the fact that there is noise, that we will be able to identify the real system, the real order. We are just able to identify the part of the system that it's most visible, if you'd like. That is where the response is most important. Now, for those that are not in the dynamics class, or just in case, imagine that the system is like this, and here are the modes. So if the system has the first mode, the second mode, the third mode, and it could go like that, right? And here is the 100th mode, if the system was very big. Now, the energy that there is in the, how do I describe it exactly? The output can be viewed as being contributions from the different modes. And it may be that, we have something like this, and by the time you get to the 4th or 5th mode, there really isn't hardly any contribution from those modes to the output. It doesn't mean that the modes don't exist. It's just that they do not add anything that matters to the output. If you'd like, you could think about it as being something like this. You want to create a certain, how should I say? No, maybe that's not a good idea because the basis is small. I was going to use this analogy, which is not great, but you wanted to create a very precise color, right? But when you want to create that color, you might say, once I put this much blue, this much red, and this much white, I got 98% of the color I want. The other 2% requires me to do a bunch of other stuff, but the bulk of it I get with just these 3. In the same manner, you can say that the output Y, okay, which we observe, it's really the sum of the contribution from all the modes. And if the structure has many modes, theoretically and in reality also, they all contribute. But by the time you get to high enough modes, the contribution of those modes to the output is no bigger than the noise. In fact, it's sometimes smaller than the noise. So there is no real hope to identify those modes. So we normally are not pursuing in real life the real system order, but an order that represents the modes that we can identify. Okay? Now, I'll put back the hat of academics here and just say, for our challenge problem and so on, the order is very small. So in those cases, we can identify everything. Okay, I'm just talking about if you went to the John Hancock Tower that has, 60 floors and 3 degrees of freedom per floor, so there's 180 modes or something. If you put sensors, maybe you could identify 12, 14, but not 100 and whatever, right? Okay, so from data, we have observer Markov parameters. You are the user, So you must specify a P. Now, let's say, you know, if you took P equal to 20 to 40, it's already going to be very large. You will not be able to identify P times M modes. So P 20 to 40, something like that, is already a very significant overkill. Now from the observer Markov, but it doesn't matter, doesn't affect the results. Now from the, it just means that the zip file is not as efficient as it could have been. Now from the observer Markov parameters then, we extract Markov parameters. And that's the unzipping of the file. When we extract Markov parameters, the user has another decision, which is how many. And in the programs that I gave you that are posted, that number I believe it's called N1. That's how many Markov parameters we want. Again, you cannot select too few because then the Hankel matrix cannot be formed adequately. But you can select more and it doesn't make any problem, any difference. So typically, I mean, I could derive a formula that tells you what is the minimum number, but typically I don't even calculate them. I mean, if you select, let's say, on the order of 200, you know, to 300 Markov parameters, that's usually more than enough for any practical problem in forming Hankel matrices. Then from the Markov parameters, what do? We then organize the Markov parameters into the Hankel matrices. So we obtain the Hankel matrix H0 and the Hankel matrix H1. Okay? The size of these matrices depends on how many Markov parameters we extract here, and they are selected automatically in the code. From the Hankel matrices, then a procedure named ERA, which we described in class, is the eigensystem realization algorithm. From the eigensystem realization algorithm, then, we obtain the system in discrete time, the discrete time model, which is A discrete, B discrete, C discrete, and there might even be a D, which is often 0, but it could be that we get a D, right? In case that we are measuring accelerations and the loads are collocated with the accelerations, there could be a D. So we have the discrete model, and then from the discrete model, we perform a D to C, which is a discrete to continuous, which is the reversal. And from here we obtain A continuous, B continuous, C continuous, D continuous. And so, in my mind, I think we are clear. We've applied this, and we basically are here. I may have mentioned something about this aspect, but this is where I'm starting now. So I'm assuming that I took my data, I obtained my observer Markov parameters, I obtained my Markov parameters, I formed my Hankels, I performed the ERA, and I have AD, BD, CD, and DD. So I now wish to do the D to C. So I am going to erase the board to have room to put the equations for the D to C. So I said this thing is kind of a mess. So usually after erasing one has to clean. This was not too bad this time. Let me check something here. -1. Yeah, okay. So we are doing the D to C, discrete to continuous. The A in continuous time, it's related to the A in discrete time, if you look at the derivation, oh, sorry, I was going to write the formula for A. Let's see. A in continuous time happens to be the logarithmic matrix, if we're using MATLAB notation, of A discrete divided by delta t. So that's how we go from the discrete time matrix to the continuous time matrix. The B continuous relates to the discrete. These formulas that I'm writing are just simply the backwards of when we derive the forward matrices. The B continuous, if you remember, I said B continuous is equal, I'm sorry, B discrete was B continuous times delta t, approximately, right? So if I had used that formula, B continuous would just be B discrete divided by delta t. And that would not be too bad, but we can do better, and if we use a somewhat more precise formula, then we get something like A continuous to the minus 1 times A discrete minus the identity multiplied times B discrete. Just double check that this is, didn't get the order wrong or anything. No, this is wrong, this is wrong. That's in the reversed order, sorry. Or is it? Right, this is the formula that I wrote, locally that I checked, is the formula for B discrete in terms of B continuous. So this is B discrete in terms of B continuous. So from there, we can derive the formula for B continuous if we have B discrete. So multiplying times AC on both sides, pre-multiplying, we would get AC times B discrete. And then we pre-multiply by the inverse of this. And so we get A discrete minus the identity to the minus 1. And this is what is B continuous as a function of B discrete. So let me put it here. B continuous equals A discrete minus the identity times A continuous. Wait, that's to the minus 1, right? Yes. I'm being very sloppy. Very sloppy. Wait a second. Start again this part. So, again, B discrete, because I think I just made an error as I was writing it down the second time. So B discrete is the inverse of A continuous times parentheses A discrete minus the identity times B continuous, right? A discrete minus the identity times B continuous. From that formula, we first multiply by AC and we get AC times B discrete. Then we multiply by the inverse of this. So that's A discrete minus the identity to the minus 1. And that is what is B continuous. Okay? Now, I'm just looking to see what I did here. Okay, correct. Where is this? Okay. So now I'll erase this. Put this more clearly here. B continuous equals A discrete minus the identity to the minus 1 times A continuous times B discrete. Okay. That formula, by the way, you can check it using just the simple one. It will work almost exactly the same. That formula is valid for what we call the zero order hole, which means that we assume that the load between time steps is flat. So if the load between time steps, within a time step, of course time steps are very small, but if the load within time step is assumed to be flat and to change like that, then this is the exact formula that connects the continuous to the discrete model. So we have A continuous and B continuous. Now C continuous is just C discrete. And for the zero order hole, it also turns out that D continuous is also the same as D discrete. So that is what the D to C part of the problem is. We finish our identification in discrete time, we get the continuous time matrix, the continuous time B, the continuous time C, the continuous times D. Okay. Now, we arrive at the part that we really want for our model updating as follows. I could just give you the answer, but let me go back a little bit so that you can be clear on the theory. So remember that our equations are like this. The state space model is this. X dot, where remember X is displacements and velocities, right? So X dot is A, X, B, F, Y is C, X, D, F, where D may be 0. Now, the first thing we want to do to really understand what we're doing here is to break the A into its spectral decomposition. So A, if we wanted to decompose that A into a triple product using the eigenvectors and eigenvalues, remember this. Any matrix multiplied times its eigenvectors, it's equal to its eigenvectors multiplied times its eigenvalues. So this is the matrix of eigenvectors, and this is the matrix of eigenvalues. The matrix of eigenvalues is just a diagonal that lists the eigenvalues in order. Okay? This is the eigenvalue problem, where we are listing all the mode shapes at the same time and all the eigenvalues at the same time. Okay? For a single one, it would just be AC times one mode equals that one mode times its own eigenvalue. For all of them, it's just this. Now, if that is true, then it follows post-multiplying times the inverse, that AC is equal to phi times lambda times phi to the minus 1. And we've done that in class several times early on, right? So that's the decomposition of AC. We now take the equation of AC decomposed and place it in the equations. And we get x dot, the derivative of the state, is equal to phi times lambda times phi to the minus 1 times xt plus bc times ft, right? And we don't have to do anything with the second one at this point. Now from this equation, now let me pre-multiply both sides times phi to the minus 1. And so we get phi to the minus 1 times x dot t equals lambda times phi to the minus 1 times xt plus phi to the minus 1 times bc times ft, right? Now you can see here that we have phi to the minus 1 x dot and phi to the minus 1 xt. So what we will do then is simply say, let's give a name to phi to the minus 1 xt. Let's just call it yt, right? Because that's just a matrix multiplied times the state, just gives me another vector, right? So in that form, this becomes y dot t equals lambda times y of t plus, now this is phi to the minus 1 bc. We normally call that tau, or I call it tau. So that's tau ft. Now the output equation, y of t, is c sub c, right? xt. But what is xt? xt is phi times yt, right? Therefore, yt, the output, is equal to cc times phi times yt plus dc times ft. Okay. Now, let me, where is the thing to erase? Let me erase to give some space and clarity. This is important, and this is important. So I'll copy them here again. Y dot of t is equal to lambda times y of t plus tau times f of t times, and I'm sorry, and y of t is equal to, okay, now instead of cc times phi, let's call this phi times yt plus dc ft. Okay? Remember that our original was x dot t is equal to ac xt plus bc ft, and yt was equal to cc xt plus dc ft, right? All we've done here is that we've made the substitution. Xt ultimately is this. Right? So, okay, there's something else. I erased it, but you can see that, well, I'll derive it again. AC times phi, we said was equal to phi times lambda, right? So, if we want, we can say that lambda is equal to phi to the minus 1 times AC times phi, right? Okay. So that's it. If you only have What do you have when you're going to do system ID? When we said we get the thing and we get observed Markov parameters, and we get Markov parameters, and we get the Hankels, and we only had ft, right? And we only had yt. So in system ID, knowing ft and yt, we are trying to obtain the system. But look at those equations were the original. Look at these equations. ft, and yt, right? So these two systems, as far as when we're doing the system ID, are exactly the same. How do I know when I get my identification that I am getting AC or lambda? How do I know that I'm getting CC or phi? How do I know that I'm getting DC or DC? That one is the only one that I'm sure, right? How do I know that I'm getting tau or BC? Actually, it's not that you don't know, it's that you really ultimately don't care. Why? Because the matrix AC, BC, CC, and DC provide a map between the input and the output. And the matrices lambda, tau, phi, and DC provide the same map between the input and the output. Therefore, the matrices of a realization, these are when we say a realization, by a realization we mean A, B, C, D with the appropriate subscripts, discrete time or continuous time. So the matrices of a realization are not unique. Okay? They're not unique. But, let's see. You can see from this expression at least that the eigenvalues of A, which are these, are obtained by doing what to the matrix A? Multiplying it times phi to the minus 1 times phi, right? This is what we call a similarity transformation, right? So what is a similarity? If I have a matrix A and I take and I do this, t to the minus 1 at, then that matrix, let's say, is B. These two matrices are said to be similar. Not similar in the sense that they look alike. It's just a technical term. If one matrix and another matrix are related by the pre-multiplication times an inverse and post-multiplication times the matrix, the two matrices are said to be similar. We can see that AC and lambda are similar matrices, right? What I need to show you now, well, do I? No. I guess this was not perhaps the best order, but it's not too unclear, I think. What I'm going to show you is that when we get the AC, we can then decompose it, and that's going to be lambda, no matter what the AC is. But I think it may be clearer if we first look at this alternative, not alternative, but parallel derivation. So this is copied, is clear, right? Oh, by the way, no, I'm going to say from this. No, I'll get back to it. I don't want to confuse you. So let's start again here. Let's start there. Now, let's assume, not assume, let's prescribe that x is equal to t z, where t just has to be a square invertible, right? As long as t to the minus 1 exists, then having x or having z is the same thing, right? Because if you know z, you know x. If you know x, you know z. Now, if we substitute this equation here, it leads to tz dot is equal to az tz, right? Plus bcf. And if we substitute it here, we get c is equal to cc times tz plus dcf, right? From the first equation, pre-multiplying by t to the minus 1, we get that. And we get this. Now, this is a particular case, a more general case of what I did before with the fees. Again, here is f, which is the input. Here is f, and here is y. The form is identical to this one. So, what that means is that when we perform a system identification, this is now should be clear. When we perform a system identification using some inputs and some outputs, we don't actually get A or B or C or D. We get this. So what do we get? We get t to the minus 1 ACT, right? For some t that we don't know what it is in general. Okay, that's the point. You do system ID, I do system ID, Bill does system ID. We all have the same input and output. But when we're finished and we are asked what is the matrix A, our A's may actually be different, because depending on some details that don't matter right now, we may have manipulated the stuff such that we end up with a T that is different for somebody and from somebody else. So this T is unknown to us. So this is the A that we get. And the B that we get is really t to the minus 1b. Is that t to the minus, for some t, right? Now what is the C that we get? Well, we get cc times t for some t, right? The only thing that we all agree on is dc, because that doesn't matter on the t, which is the transformation. That puts it in some bases that we don't know. At this point, it doesn't look so great. Okay, so it's not the same A, it's not the same B, it's not the same C. So what do we really know? Well, remember the Markov parameters, right? What was the form of the Markov parameters for Yj? I think you guys know it now. In continuous time, it would be Cc in discrete time, but it's the same thing in continuous time, something like this, right? That's the way the Markov parameter writes. So now let's substitute to see what the Markov parameter looks like. If we say we really don't know C, we just know some C. So the some C that we know is this. And we say we don't really know A, we just know some A, right? Which is t to the minus 1 times AC times t to the j minus 1. And we only know some B, which is t to the minus 1 times BC. What?
I'm looking for the keys. I thought I might have.
Yeah, you put them here somewhere.
You saw them, right? Well,
Yes.
they're right here.
So you see that this is the Markov parameter, right? Now, if we take the sequence that we have here, imagine that J was, I don't know, 3. So that means this would be raised to the second power, right? So the Markov parameter 3 would be Cc times t, and then this t to the minus 1 ACT times t to the minus 1 ACT, right? That would be a 2. Then times t to the minus 1, then times BC, right? So that's the way the Markov parameter in general would look. So you can see that t and t to the minus 1 is an identity, t and t to the minus 1 is an identity, and t and t to the minus 1 is an identity, and therefore the third Markov parameter is CC AC squared times BC. Therefore, the Markov parameter does not depend on t. That's why we can do the system ID using the Markovs, right? Because they are not a function of the t. So we take the Markov parameters, we organize them in the Hankel matrices, we have from there go and so on. Now we say, okay, cool, so we've got these generic A's, and so we accept that all we have is some A, which is t to the minus 1 times AT, some B, which is t to the minus 1 times B, some C, which is equal to C times, what did I call it, phi like this? Yeah, probably use that notation. And we have some D, that's the only one that doesn't matter. Okay, so this is all we're going to get from a system ID. We don't know what the T is. But we see that this is a similarity. And therefore, no matter what the T is, what we get is a similarity on the A. And we know that similarities do not change eigenvalues. Therefore, we can calculate the eigenvalues of whatever A we got, and we're all going to get the same thing, even if we had different A's. Okay? Finally, it is possible to show that these are the eigenvectors at the measured coordinates. Where this phi, in case I change the notation, is such that A continuous times phi is equal to phi times lambda. So these are the eigenvectors of the A. When they get multiplied by the C, you get this together are the eigenvectors of the measured coordinates. Okay? Yeah, this is what I called the big phi before. Okay, so, okay, I think I'll do this. And I will say, okay, I'm going to show you with a numerical example, even though it's very simple, so you can see it. But therefore, when we finish the ID, we have A discrete, B discrete, C discrete, and D discrete, right? Then we do the D to C, and we have A continuous, B continuous, C continuous, D continuous. And then now, what we do is solve. Solve the eigenvalues of AC. Let me say there were 4. So when you get, if there are 4 eigenvalues of AC, that means your system was of order 4, and that was determined by the number of singular values when you looked at the Hankel matrix, right? Remember, the order is the number of not equal to 0 singular values of the Hankel. So at this point we already know the system order, right? And now we do our eigenvalues, and these are the lambdas. Okay. In general, these eigenvalues come in complex conjugates. So lambda 1 and then lambda 2 is equal to the conjugate of lambda 1. Then you have lambda 3, and lambda 4 is the conjugate of lambda 3. So for systems that are underdamped, that is the situation. The eigenvalues come in complex conjugate pairs. So for example, if lambda 1 is minus 3 plus 10i, then lambda 2 is minus 3 minus 10i. Okay? That's how the eigenvalues come together in pairs. Let me stop the tape right now so that the file doesn't get too long, and then do a second part and finish it.